Good morning, everyone, and Jai Hind. Today we are going to see one of the solve example for linear SVM. So before going into the details of the SVM, the first thing that we need to know about the SVM is that it is one of the most popular algorithms, and it is a supervised learning technique, meaning in the data set you have to have the class labels with you to train the SVM model, and this is used in both of the situations. If you want to do some classification, or if you want to do regression, in both of the cases we can use support vector machine algorithm. And primarily it is used for solving the classification problems in machine learning. Now the goal of SVM is to create the baseline or the decision boundary or the hyperplane that we call it here. And the boundary or the hyperplane is separating the n-dimensional space into different segments representing different classes of data. And this way the hyperplane helps us in deciding what will be the label for the incoming pattern, or the pattern or a new pattern basically which is already not present inside the data set. So whenever a future data point is coming, the decision boundary actually helps in finding out the label, whether the point belongs to the positive class or it belongs to the negative class. When we talk about the SVM algorithm, the important thing to note here is the use of kernel trick. So basically the kernel function or the kernel trick is used inside the SVM classifier to find out the decision boundary. And as we already have seen in the previous lecture, that kernel trick is mapping your data from lower dimensional space to the higher dimensional space, and thereby finding out the appropriate decision boundary to separate out the observations or the points of different classes. So with this information with us, we now move on to see how we can solve some example problem, and we are able to find out the hyperplane to separate out the different classes of the data in the data sets. So for example, we are taking up some example data set here. So the data set that we are having right now, for example, the data set would be like, we are having certain points which belong to the positive class. So in positive class, for example, we are having 2 points like 2, 2, and we are having a point 4, 4. Right? Then we are having 2 points in the negative class. So for example, the negative class points are like this. We are having one at 4, 0. The other one is at 0, 0. Now the first thing in the support vector machines is that we need to find out that where are the support vectors, right? So as we already know about the algorithm, that the support vector machine uses find out the hyperplane location with the help of the support vector. So the first question here is how to find out the support vectors. So we are going to see the illustration here to find out the support vectors. In this way, what we are going to do, that we are going to plot the points in a 2-dimensional space. So for example, if I plot these points here, and suppose I'm marking like this, 1, 2, 3, 4, this is the x-axis, and this is the y-axis. I'm keeping up 1, 2, 3, and this is 4. Now the first point is at 2, 2. So on x you are going 2, then on y you are going 2, and at the intersection of here there is 1 point. Now one more assumption I'm taking up here, that when I'm plotting the points of the positive class, I will represent them, for example, by a cross, and when I'm plotting the negative class points, I will represent them with a circle, right? So since the first point 2, 2 is belonging to positive class, so I will mark a cross here. Then the second point is at 4, 4. So at 4 here and at 4 here, somewhere here, we are having another point of positive class. Now, in case of negative class, the first point lies at 4, 0. So on x-axis, it is 4 and on y it is 0. So the first point of negative class lies here. Then the other one is at origin like this. So this is the visualization of the support vectors, the data points here. And from this visualization, I need to find out that where are the locations of the support vectors. Now, if we know the definition of support vectors are the points of one class which are the closest or nearest to the other class points. So with this definition, we can see that for the positive class, the point which is closest to the negative class points is this one, right? So this becomes the first support vector for us, and I will name it as S1. So for the positive class, I have already found out one of the support vectors here, and no other point is closest or closer as compared to this point with the negative class point. So this is one support vector only belonging to the positive class. In case of negative class, there are 2 points. One point is here and the other one is here. And as we can see that both of these points, they are almost at equal distance from the positive class point. So we are taking up both of these as the support vectors in this case. So these become the support vector 2 and support vector 3 for the negative class. So now finally what we have, that we are having 3 support vectors in this case, S1, S2 and S3, right? We will write down the support vectors, and by before writing the support vectors here, one more thing I have to do is that I need to augment one value to each of these support vectors. So previously, if we know that the support vector points, how many we have found out? We have found out 3 support vectors here. The first vector is at 2, 2, right? So 2, 2, this is S1. Then these 2 are S2 and S3, for example. Okay, this is S2 actually, and this is S3. So this way, 3 support vectors are there. Now we are going to find out the augmented support vectors from these support vectors. So so what we are going to augment into these support vectors to make them augmented support vectors. So for this, we are assuming again that the value of bias we are keeping here as 1. Okay, so we are taking a bias value or assuming a bias value for now. Actually, we have to find out the value of the bias, the final value, but right now we are taking an assumption here, and according to this assumption, we are keeping the value of bias as 1 here, and we will append this bias value to each and every support vector only. Okay, so this way, now, for example, the first augmented support vector, augmented support vector, that I'm getting is like this. So my first augmented support vector, which I'm denoting by S1 tilde. I'm keeping a tilde here so that I'm able to understand that this is the modified or the augmented support vector, not the original one. So the support vector 1 was having originally the value 2, 2, and now I'm appending the value of bias here as 1. So I got the first augmented support vector. Now same way I can find out another augmented support vector. For S2 the value was 0 0, so appending 1 gives us a 0 0 1. This is the next augmented support vector. Similar ways we can find out support vector 3 from 0 4 0. We are appending 1 as the bias and we are getting another 1. So this way 3 augmented support vector we have found out. Now an important question here is that when we are studying the SVM algorithm, we know that SVM applies a kernel trick, and basically how the classification algorithm works in case of linear SVM, that it is mapping or transforming or taking up the data from lower dimensional spaces to higher dimensional spaces to find out the best possible boundary that can separate out the points of different classes. So where the transformation from lower to higher dimensional is done. So as you can see here, when you are augmenting a bias value to the support vector, you are actually elevating the dimension of this point or elevating this point in the space from lower dimension to higher dimension. So previously, if I see the original support vector was a two-dimensional point, we are having x value, we are having the y value, right? So this was in a 2D plane. Now when you appended another point here, another value here, so in a way we can see that this bias is now acting as a third dimension which we have appended here. So now your same support vector is mapped to a 3D space, and you can assume that this bias is nothing but right now it is the z direction of the three-dimensional plane, right? So this way we have elevated each and every support vector point to a higher dimensional plane. Now what I need to do next, after finding out the support vectors, I need to find out the location of the hyperplane, right, in the space. So for finding out the location, what I need to realize here is that these are the support vector, and between them there is a possibility of having in kind of infinite number of such hyperplanes. So where exactly my my hyperplane lies here in this plane? So for that I need to formulate the hyperplane equation, and as we know, the hyperplane equation is simply like y hat is equal to w t x plus b, right? So this is the equation of the hyperplane, and we are talking about a linear decision boundary right now. So these are the parameter of the linear boundary. So you know that y is the output here, x is the input here, and w is the weight or the weight factor, and b is the bias, right? And I need to estimate the value of the weights and the bias for for getting the value of the outcome or the y, or the label of the y, label of the point which is not already present in the data set. So whenever I'm supplying the value of x and I'm putting the value of this parameter w and this b, I will be getting the label information for this point, for this incoming point, right? So y is kind of the label or the output. Now to find out the parameters like w and b, what I need to do, right? So now in the next step, what I have to do is that I need to, find out the weight vector. Okay, so to find out the weight vector, and since we are finding out the weight vector from the augmented support vectors, let's say that the weight vector that I'm finding out right now is called as W tilde. Okay, this W tilde, because this will be of course the estimated or the augmented weight vector. And of course, to find out this W, I need to make use of the support vector, the augmented support vectors now. How the W is going to be calculated? So in the next step, what we have to do, that we have to find out some unknown variables. So I need to find out, for example, certain unknown variables. Here in this case, I have to find out, for example, the unknown variables that I am dealing with is represented by alpha. So in this case, I need to find out 3 unknowns, right? Alpha 1, alpha 2, and alpha 3. And why 3? Because we are having 3 support vectors. So for every support vector, I'm keeping 1 unknown variable here, alpha 1, alpha 2, and alpha 3, and we will finding out the value of these unknowns, right? Now, next question is how to find out the values of these 3 unknown variables. So this we are going to do by formulating some equations with the help of these augmented support vector S1, S2, and S3. And by solving those simultaneous equations, we can finally find out the value of alpha 1, alpha 2, and alpha 3, right? So first, to find out W, we need to find out value of these unknowns. How many unknowns will be there depends on how many augmented vectors you have. So if you have 3 support vectors, 3 unknown variables. If you are having 4 support vectors, 4 unknown variables, and 4 simultaneous equations you have to solve to find out the values of those unknowns. So this way we have to proceed. Now let's go to the next step. So now I need to formulate the equations for finding out these unknown variables. And first of all, the first equation that I'm going to put up is alpha 1. For example, I will write alpha 1 plus alpha 2 plus alpha 3 equals, then I will write alpha 1, alpha 2. I'm putting up 3 equations here. Alpha 3 equal to something, alpha 1, alpha 2 plus alpha 3 equal to something. Now, here, these unknown equations or these unknown variables, they will be making use of these augmented support vectors. And I'm assuming that for the first equation, I need to find out the dot product of support vector 1, that is S1, with every other support vector. So we are finding out like S1 dot product with S1. Then similar way, S1, S2. Then we are finding out the dot product of S1 with S3. Okay. The similar ways we are, proceeding for the other 2 equations. So now for the second equation, I will find out with respect to the second support vector. So here I will keep it like S1 dot product S2, then S2 dot product S3, then I have to find out, sorry, S2 and S2, right? So first S1, S2, then S2, S2, and then you have to find out with S2 and S3, right? The third equation, we assuming that it corresponds to the support vector 3. So you are first taking a dot product between S1 and S3, then you are taking dot product between S2 and S3, then you are taking S3, S3, the dot product like this. Okay. Now, the next question is how to find out what we have to keep here as the right hand side of these equations. So for this, we have to see that what is the label of each of these support vectors. So first equation, as we are assuming that it belongs to the first support vector S1, the second one is for S2, third one is for S3. We will see the class labels of these points. So if you remember, that S1 is a positive class point. So this is a positive class point and these two are the negative class points, right? So we will keep, for the first equation, we will equate to 1 or a positive 1, and for the rest of the two, we will equate it to -1. So this way, we have got, three different equations here. Now, we have to simply solve these equations. So we will, keep the value of these S1, S2 and S3 in these three equations, and we are able to, solve it. This is 1, equation 2, this is equation 3. So now, for example, I will write for the first one. So you will write alpha 1, S1 is 2 to 1. So you will find out 2 to 1, dot product 2 to 1 like this. Then alpha 2, this will be S1, S2. S1 is 2 to 1. Then S2 is 0, 0, 1, 0, 0, 1. Then alpha 3, you are keeping again S1. S1 is 2 to 1. And you are taking the dot product of this with S3, which is 4, 0, 1. Right? So this is the first equation. Right? Similar ways I can write for the other equations. So for alpha 1, now in the second equation you will keep S1 S2 again. So S1 S2 is like 2 to 1 dot product 0, 0, 1 plus alpha 2 and alpha 2 S2 S2. So S2 is 0, 0, 1. So you are calculating 0, 0, 1 dot product with 0, 0, 1 like this. Then alpha 3 and alpha 3 you are calculating like S2 S3. So S2 is 0, 0, 1 and S3 is 4, 0, 1. This becomes the second equation. Now for the third equation, you will write alpha 1, S1 is 2 to 1, 2 to 1, and you need to find out the dot product with S3. So S3 is 4, 0, 1 plus alpha 2. Alpha 2, you are finding out S2, S3. So S2 is 0, 0, 1 dot product with S3, 4, 0, 1. Then alpha 3 you are getting from here S3, S3. So S3 is 4, 0, 1, finding out a dot product with 4, 0, 1 like this way, right? And that way, equals to -1. This will be equal to -1. This will be equal to +1, right? So finally, solving all this, we are going to get the value like 9 alpha 1 plus alpha 2 plus 9 alpha 3 is equal to 1. And then we are having the next equation, alpha 1 plus alpha 2 plus alpha 3 is equal to -1. Then 9 alpha 1 plus alpha 2 plus 17 alpha 3 is equal to -1. So the solved equations or the simplified equations will be like this, right? Now you finally have to solve these equations. So we are solving these simultaneous equations, and then finally we will be getting the value of alpha 1, alpha 2 and alpha 3. So in this case, when we solve, alpha 1 will come to 0.5, alpha 2 will come to -1.25, then alpha 3 will come to -0.25. Now once the value of alpha 1, alpha 2 and alpha 3, these unknowns we got, we can now finally find out the value of the augmented weight vector, which is W tilde. So now to find out the value of W, I need to simply use alpha I SI like this. Right? If I expand this, so this will come to, for example, alpha 1 S1 plus alpha 2 S2 plus alpha 3 S3. Okay, and this will come to, for example, this will come to 0.5 multiplied by 2 to 1. Then alpha 2 is minus 1.25 multiplied by S2. So S2 is nothing but 001. Then we are having plus minus 0.25 and the S3. So S3 is 401, right? If we solve this, so in the first step, we are solving it component wise, for example. So I will get like, for example, 0.5. Then you are getting 0 minus 1.25 and plus minus 1 0 minus 0.25, right? Further solving it and finding out, component wise, if you keep it, then you will get the W as 1 plus 0 minus 1, then 1 plus 0 plus 0, and then we are getting from this, we are taking this component, right? So you will get 0.5 minus 1.25 minus 0.25, and when you solve this, this will come to 0, this will come to 1, and this will come to minus 1, right? So finally we got the augmented weight vector, which is W tilde, and we got it like 0, 1, 1. If you remember correctly, or previously, that we have appended a bias value at the end of these support vectors. So now to find out the value of W, we have to remove this component. Okay, so this is nothing but the value of bias in this vector, and this is the value of W, original W. So now you can see that W comes to 0, 1, and value of bias comes to minus 1, right? Now the next question is, after finding out the value of the weight vector and the bias, how to draw the decision boundary. Okay, so here you can solve it further. So for example, the original equation was WTX plus B is equal to 0. This was the equation of the hyperplane that we have used initially. Now, for example, if I keep the value of weight vector, which is 0, 1 multiplied by value of x plus this bias is minus 1 is equal to 0. So this will come to 0, 1, x minus 1 is equal to 0, right? And x again is a is a point in two-dimensional space. So you can further break it down as x1 or x and y. For example, in our case, we are taking the single point in a two-dimensional plane. So your point or your x is nothing but a vector representing the x and y coordinates, right? So now you can simplify it further by writing, for example, you can write 0 x1 and this becomes y, or 1 y minus 1 is equal to 0. Finally, this becomes 0 and y is there. So you can see that y is equal to plus 1. Okay, so y is equal to plus 1 is the location of the decision boundary in a two-dimensional plane. Okay, wherever you are keeping y, so on y you have to take up or go to point corresponding to 1 or plus 1, and from here the boundary is drawn, right? And all the points which are falling below here, okay, they belongs to the negative class, and all the points which are having value greater than this, they will be falling into the positive class. So this way the whole process is done. and you are able to find out the location of the hyperplane. So with this, we end up here today. Thank you very much.